So, hi everyone, and thank you so much for coming to our colloquium today. So this morning we have Balu, our speaker from University of Melbourne. And Balu is PhD student, and Balu is now at the final year of his PhD, and will submit your thesis soon in 2-3 months.
Soon.
Yes, and so basically his research focuses mostly on the early phase of the universe, the epoch of reionization using simulations of the H1 21 centimeter emission. And today we were talking about hydrogen in the first billion years. But before that, Stu, would you please to give a few more words?
All right. Yeah, it's great to have Balu here today. So Balu's been a student for 3 years nearly, and he's nearly 4 years actually. Yeah. But he's distinguished in 2 ways that I can think of right now. One of which was getting off essentially the last plane that got into Australia.
This is true.
Before lockdown, I think he landed at 11 o'clock at night, and the next day they closed the border. So that's kind of that maybe that was lucky. Got in. He wouldn't have got in for a long time otherwise, but it also meant that he met us for one meeting on the Monday, and then we all went into lockdown in Melbourne for months. So Balu had a bit of a rough start to life in Australia, but and made the most of the Melbourne lockdowns. But despite this, has done very well. And I'll let him tell you about the science. But the other distinguishing feature of Balu's PhD is that he's done the calculation that was kind of the motivation for my laureate fellowship, which was finished 5 years ago. So if I hope that our laureate fellows here at the ANU are more efficient than the ones of the past. But so needless to say, I'm very happy with the outcome of this PhD. Balu's done a good job, and take it away.
Thanks, Juan here. Yep. So my name is Balu. I'm a final year PhD student. Planning to submit by January. And as I said, Stu, Stu mentioned, I had the full lockdown experience in Melbourne. So today I'll be talking to you about the hydrogen in the first billion years. So I spent my my PhD looking at simulating something on the epoch of ionization or the EOR, and my official supervisors are Stu and Brad. So by the end of this talk, you hopefully will know what the EOR is and why do we care about EOR as well, and how you can actually simulate this in a laptop. So this does what? Okay, yes. All right, so if you are, so you have the formation of the CMB after the Big Bang and the inflation and other things. So you have the formation of the CMB here. Now, if you were around here in the universe at that time, if you had looked around, the universe would have been fairly boring, in the sense that you wouldn't be able to see any luminous sources. So you don't have any stars, you don't have any galaxies or anything. But even if you have these stars and galaxies, you actually won't be able to see them, because the IGM here at this time is actually opaque, especially because the galaxies emit a lot of UV photons, and since the IGM, the H1 atoms in the IGM is actually very, they scatter the UV photons, you actually won't be able to see anything through the IGM fog, so to speak. So that's happening here. Yes, and now if you move to the local universe and you look around, you see stars and galaxies. Now, most of the stars you see are actually the stars in our own galaxy, but that's fine. But you also see the galaxies. Now, what that means is that the IGM is actually now transparent, so you're actually able to see the photons which are emitted by this galaxy in your local universe. But it's also true that as you look deeper and deeper into the universe, you're also seeing back in time. So as you point your instruments from here onwards towards the left, you see that after some time you see a drop in the number of galaxies you see. Now there are two reasons here. So you're looking back in time. So you're looking at a much younger universe. So you don't have as many galaxies. That's fine. But even if you compensate for this fact, you see that you're not seeing enough galaxies as you expect. Now so that happens somewhere around here. So that's when you have the formation of the first stars and galaxies. So what you can basically infer from these two observations is that the IgM has actually gone from an opaque to a transparent state somewhere around here. Now, to understand what's happening here, we need to look at the basics of cosmology. Yeah, so here we are looking at dark matter only and body simulation. If you look at these pink dots here, so that's where you have the formation of the so-called stable dark matter halos. And in the standard model of cosmology, we know that the baryons basically follow the dark matter distribution. So what happens is that they will actually flow into these so-called dark matter halos, and the gas will essentially cool down, and you will have the formation of the galaxies. And obviously, the only thing is you can actually observe in a manner are these luminous baryonic sources. The other thing which I wanted to keep in mind is this spot here. So even if a dark matter halo is actually able to hold on the gas, it's not guaranteed that the gas will actually cool down to form stars. So you need to have a minimum mass for this dark matter halos, so that the gas can actually efficiently cool down. So depending on the way this gas basically cools, you have different mechanisms. So at the top bar here, you are looking at the smallest mass of this dark matter halo, where the baryons can actually cool down to form galaxies. So in my PhD, I basically only looked at this so-called atomically cooling galaxies. So they have a mass of 10 to the power 7 in units of solar mass. So what actually happened here is that you have the formation of the first stars and the first galaxies, and these galaxies will emit a lot of intense UV photons, and they will basically what they will do is that they will actually carve out H2 bubbles in the IgM, and as time goes on, these bubbles will expand, and they will fill the entire IgM of the universe. So here we are looking at a simulation from our team, where we are so this plot here is a 2D slice of this same simulation here. So these white dots are the first galaxies and the first stars, and the red color is essentially the IgM. So as you can see, as time goes on, you have the formation of these H2 bubbles in the IgM, and they will basically expand and fill the whole universe. So what we are looking for in your 21 centimeter cosmology is, instead of looking for the stars and the galaxies, we are actually going to look at the IgM emission. So if you want to look at the IgM, and especially if you want to look at the H1, what you do in astronomy is that you look for something called the H1 signal. So if you look at the Voyager golden records cover, you see these symbols here. So, and if you zoom in, you see this schematic. So if you look at the neutral H1 atom, the proton and the electrons have spins, and the lowest end of the state is when they are anti-parallel to each other. And but they can also go to an excited state where they're actually parallel, and the energy difference between these two energy levels is actually of the order of lambda equal to 21 centimeter in wavelength. So if you want to look at for H1, we need to look at the H1 21 centimeter signal, as I'm sure most of you know. So what you do, what you actually measure in your 21 centimeter cosmology is something called the brightness temperature offset. So the main term here is this TS, it is a spin temperature minus a background temperature of T gamma. And we almost always assume gamma equal to the CMB temperature. Now, if you want to look at this long equation, there are a few things happening here. So, so this is essentially an extra correction term because your IGM can have a velocity which is on top of your Hubble flow. So we will not talk about that. This is also like a small correction term. But the main terms here are this XH1, which is a neutral fraction, and this term here, the spin temperature, and also this last long term here. So what you actually do in 21 centimeter ER is that you know your cosmology from your CMB experiments. So now once you know your cosmology and this TS and also the XH1 basically depends upon the luminous source in your universe. So if you know your cosmology and you observe the signal, you will actually be able to say something about this first luminous sources. So this term here basically says that you need to have a certain amount of H1 in the IGM, because if this term goes to 0, you won't be able to see anything, obviously. And this TS term basically is a proxy for the state of the IGM in a manner. And we'll actually talk about this spin temperature soon. So this is a signal you will look for. All right. Cool. So if you look at the CMB sky, for example, you will look at the sky and it's actually a very uniform sky. So the 0th order information you can ask for the CMB is the temperature of the black body spectrum. So that's your 2.7 Kelvin value. And the other thing you can do is you can subtract out the mean in a manner. Then you can talk about the fluctuations of the emission on the sky as a function of scale. And that signal is your CMB power spectrum. So, but the other thing is that you only have one CMB sky in a manner. While if you want to look at the 21 centimeter sky, since you have since the 21 centimeter line is actually line transition, you can actually go to a different value for Z. So instead of having one mean value, you can have means as a function of Z now. So that's a signal on the left-hand side. So all you do is you look at the you look at your 21 centimeter sky, then you look at the mean value, and something else you can do is that you can subtract out the mean, and you can look at the fluctuations on the sky as a function of k, which is your scale on the sky. So that's the 21 centimeter power spectrum. And now since you have more than one skies, you actually have more than one 21 centimeter power spectra now. And so why do we measure these things? So the main reason we look at the signal is that depending on your sources, you have different effects on the signal. For example, Early on, the signal will be dominated by the laminar photons, and you will have the domination by the X-ray photons, and later on, you will have the impact of the UV photons as well. So this is a model of what you expect to see. So for example, this heating phase is when you have the impact of the X-rays on the signal. So this is why we observe the 21 centimeter signal. So where do we stand in terms of the observations? So this is okay. So if you look at this curve here, so this is showing you the one of the signals which are supposed to be observed by the edges, and this was published 5 years ago, but nobody has actually verified the signal yet. So people, especially in the simulations community, we are not actually confident about the actual signal here. And on the right hand side here, you are looking at upper limits for your 21 centimeter power spectrum. The main takeaway from this one here is that if you look at all the models, they are all down here, and all the observations are at the moment upper limits. But as you can see, as newer and newer data comes online, we are actually going downwards in this axis here. So we should be observing the signal in once the SK actually starts observations. That's the hope anyway. So what we do in our team is that we make simulations for this signal. So the main issue here is that we are looking at H2 bubbles of 10 megaparsecs, and we know that a 1 megaparsecs volume can basically have thousands of galaxies, I think. Yeah, so if you look at a small portion, you have numerous galaxies, and if you want to simulate your simulation volume should be large enough to have a large number of H2 bubbles. But these H2 bubbles are actually sourced by these galaxies now. And we also know that the actual sources are not the galaxies themselves, but you also need to look at the formation of stars as well as the feedback from supernovae. So if you want to simulate this, from the basics, you should have a large simulation, but you should also be able to resolve all the small galaxies as well. And that's actually insanely hard to do, obviously, which you will agree with me if you do simulations. And so there are different ways to do simulations in your. So you can do the very basic paper pen calculations, but you also need very physics-rich hydro simulations over here. But the issue is that when you want to do a hydro simulation of large volume, you won't be able to explore as many of your underlying parameter space. So what we do in our team is somewhere between so-called semi-numerical as well as n-body plus RST. So what we do is something called the semi-analytical modeling, which lies partway between semi-numerical models as well as full hydro simulations. So our model is called a MER-axis, and as I said, it's a semi-analytical model or SAM. So the way SAM works is that you have a pure dark matter only n-body simulations. Then you extract the dark matter halo information from the n-body simulations, and you run a SAM on top of these n-body simulations. So you don't have any galaxies. So the galaxies are actually introduced by MER-axis here. So we have a very detailed implementation for EOR, for star formation, supernova feedback, agents, and etc. Now, what makes meta-axis interesting for the EOR community is that we also have a modified version of a semi-numerical code called 21 centimeter fast. I will explain how 21 centimeter fast works fairly soon. And for fans of Game of Thrones, meta-axis is actually the name of a Targaryen dragon. So when you actually look at the source code, you have functions like this, which is the main function within a meta-axis. All right, so the way 21 centimeter fast works is something on the excursion set. For formalism, it's actually very simple. So what you do is you go to a galaxy, you consider a volume around that region. Then you look at the amount of baryons which are in the form of stars. Now you go from the number of stars, number of baryons in the form of stars to a number of UV photons. That's fine, but you also know the number of total baryons in the same volume. So you basically look at the number of UV photons and the number of neutral H1 atoms. So that's how you do the excursion set for the EOR morphology. All right, so what did I do? So for my PhD, as I mentioned, we need large volumes if you want to simulate EOR. But now that's because your H2 bubbles are of the order of tens to of megaparsecs. And you also need large volume because if you want to look at the impact of X-rays, because since X-rays have fairly long mean free path, you should have at least a few mean free paths within your simulation volume. So, so the X-rays have of the order of 100 megaparsecs mean free path. But the issue here is that as you go to a larger and larger volume, you won't be able to see smaller and smaller halos. Now, if meta-axis don't see these halos, you won't be able to populate galaxies into those halos. And consequently, you will actually miss out on the impact of these halos or these small galaxies on the EOR morphology. So if you want a higher resolution in the sense that you need to see these small halos, you need a more number of particles for your parent and body simulation. Now that's actually not easy to do. So what we do is something called augmentation. So what I did for this one, yes. So I'm introducing a simulation called L210 over here. So that's a pure embodied simulation. It's a fairly large volume of our 210 over H megaparsecs on a site. So here you're looking at the resolution of the, so this is the smallest halo mass. It's this simulation can actually see in a manner. So that's this orange curve here. And this line here, so as I mentioned, this is the mass of the dark matter halo, which is actually capable of hosting a galaxy. As you can see, if you run the simulation, if you run meta-axis on this L210, you are essentially missing out all the galaxies which essentially fall here. But so what we did was we actually introduced smaller halos into the box. Such that this new box, which I'm calling L210 Aug for augmented, is actually the same volume simulation, but we are actually able to go to much lower halo mass resolution now. This L210 Aug is a simulation of almost 1 trillion particles, which is insanely hard to do. So that's what I did for my PhD. And if yeah, so here we are looking at all the simulations which I'll be talking about. So L210 and L210 Aug are the same simulation, but the L210 Aug is the augmented one. But they have the same input parameters for the meta-axis simulation side of things. And I'm also introducing L210 Aug, low X and high X. So they are the same as the L210 Aug, but we have more X-rays in the high X and less number of X-rays in the low X ones. Yes. This is because we wanted to explore the impact of the X-rays on the 21 centimeters signal. All right. So if you look on, on the top panel, you're looking at your ionization morphology from the augmented simulation, and the unaugmented one on the bottom panel here. So this is this blue is the H2 bubbles, and the yellow is the H1 gas. So the main point here is that you can see, if you look at the same neural fraction, you can see more number of small structures here for the augmented one. And that's simply because you have all these small galaxies. Now what I can do is I can actually zoom in here so that we can see the impact. All right, so if you look here for the augmented one, we have these small H2 bubbles that's actually hosted by this more number of smaller halos now. Now that's a which is actually seen across the whole simulation now. So at the bottom panel here, you are looking at the difference between these two panels. Now, if you remember the long equation for the Brand's temperature formula, you do have a term which actually depends upon your ionization morphology. So what this means is that you will actually have impact on your predicted simulated 21 centimeter signals now. Before moving on to the 21 centimeter signals, I will simply show this one here. We are actually looking at your history. So this is the average fraction as a function of time. The main ones I want you to look at the moment is the L2 term and the L2 term off here. So the orange and the blue. As you can see, simply because we have more smaller halos and simply because we have more smaller galaxies, you actually finish your yearly in the augmented box here. So that's a blue. And if you also look at the low X-ray and the high X-ray ones, the low X-ray ones actually lying exactly below the augmented one. While if you look at the high X-ray ones, they also finished earlier. So the main impact of the X-rays is to actually impact the spin temperatures of the gas. They do cause ionization, but that only happens for extremely large values of X-rays, which is what you're seeing here. But if you look at the 21 centimeter signal, that's where the X-rays have more impact. For example, here you are looking at the mean signal of the 21 centimeter signal from the EOR. The main point here is that if you look at the orange and the blue, simply because, but they both are the same shape, they both have the same values on the y-axis. But you can see that simply because you have more sources, we actually start the X-ray heating much earlier in the augmented one. But if you look at the X-ray ones, that's more interesting because, again, this is actually the TS minus T gamma term. So the fact that you have a much larger dip here for the low X-ray ones, that means that the TS term is much smaller than the T gamma term now. What this means is that the IGM is much more colder now, as well as if you look at, for example, for some of the high X-ray ones, the IGM, since you have more number of X-rays, they actually heat up the gas. So it is why the gas actually goes in the emission here. So that's the dark curve here up top. Right. So this is something on the H1 21 centimeter light cone. This is actually the same information as this last one, but you can also see the variations in the simulation volume because of this of the morphology here as well. As you can see again, the low X-ray one is always in the negative region, so that's the absorption phase. While for the high X-ray ones, it's almost always in the emission phase here. So for this one, we looked at, we introduced X-ray heating into the meraxis SAM. And we also looked at the importance of how, if you want to simulate this EOR, you also need to have large volumes, and you also need to be able to see all these small galaxies, because these galaxies can actually have an impact on your simulated 21 centimeters signal. So I'll just stop here for a second. I can leave it here. So for the other part of the what we wanted to do was we wanted to since we have this very large simulation, which also have a complete galaxy population, we wanted to look at the impact of, not the impact actually, yeah. So we wanted to look at all these high-redshift galaxies from James Webb. So if you look at this bottom, so this is the UV luminosity function, which is, if you look at the unit volume in the universe, how many galaxies of so and so amount of luminosity do you actually expect to see? So the meraxis fiducial simulation was actually calibrated with respect to the Hubble ones, but they are all extended from z equal to 5 to 10. So we also have the newer observation from James Webb as well here. So the main point here is that our fiducial basic model actually agrees with the UV luminosity functions for up to z equal to 10. But as we go to higher and higher redshift, we see that we are actually not able to match the luminosity function, especially for the massive, more luminous ones. That's what we showed in this work. So for this second work, we wanted to look at what you can actually learn about the EOR from a future detection of the 21 centimeter power spectrum. So it's actually a summary of my last work. I just want to point out that we have a very large simulation, which is actually able to solve all the possible galaxies. And our fiducial simulation is actually calibrated with respect to the UV luminosity functions and the CMB optical depth and so on. Yeah, so for this work, we wanted to understand what you can actually learn about the EOR from a future possible detection of the 21 centimeter PS. So for this, we need to go into what the actual way galaxy formation works within the meraxis SAM. So you have a dark matter halo and you have the IgM outside it. And this gas can actually cool down to the halo. And once it's actually part of the halo, it actually becomes part of something called the hot gas. And from there, this gas can actually cool down to form something called the gas disk. And as time goes on, you have the formation of a larger disk now. Yes, and as time goes on, you will have the formation of the stars from this large disk. So we have model parameters which actually control the amount, the efficiency of formation of stars. That's the alpha SF, but the sigma SF is the minimum mass you need for the disk, so that you actually start for formation of stars. Now, as time goes on, you will have the formation of a galaxy. And as time goes on, the stars will also go supernovae. So for example, we have the supernova heat efficiency as well as the supernova ejection efficiency. Now, what the supernova essentially does is that it actually heats up the cold gas disk. Now, most of the time, the cold gas stays within the halo. But if your supernova feedback is very effective, and also if this the galaxy is actually fairly small, some of the gas can actually go back into the IGM. So that's your epsilon naught here. That's ejection efficiency. Right. So, and you also know that the galaxies actually emit a lot of X-rays as well as UV photons. So the LX-ray, which is parameters in terms of this star formation rate of the galaxy, is basically the amount of X-rays that are emitted by the galaxy as well. And the E naught is the minimum amount of the minimum energy of the X-ray photon, so that the X-ray photon can actually escape the ISM of the galaxy. And we also have fairly detailed implementation for the UV escape fraction, because that's obviously the photon which basically sets your EOR morphology. So you have the F escape naught, which is your UV escape fraction normalization, and we also implement the UV escape as a power law in time. So the alpha escape is the power law index. Yeah, so what can you learn about these parameters of the galaxies in the early universe if you actually do observe the 21 centimeter PS now? Now, since we are actually talking about a future observations, and since we don't have any actual observations, what you can do is you can do something like a facial metrics analysis. So for this one, you assume that your model is the actual signal. So you need a derivative of your observation with respect to parameters. So the observations is your delta, which is your 21 centimeter power spectrum. And you also need a handle on your error or the noise on your signal, which you have to take into account your instrument as well. Now, the reason we do this is that under very strong assumptions, you can say that the covariance matrix of your parameters, the Cij here, is actually inverse of your Fisher matrix. So that's why you do the Fisher matrix analysis, and also because it's fairly easy to do. So for this one, we need to simulated an observations for the SK1 law for 1000 hours of observation. So this blue curve here is the fiducial 21 centimeter power spectrum from meraxis, and this ash noise is the noise from for the instrument for which is SK1 law for 1000 hours of observation. And the spin regions are the so-called K-morph, which the SK won't be sensitive to. So our actual signal is between these two white dotted vertical lines here. So once you do that, you will be able to form a Fisher matrix, and you can invert your Fisher matrix to get your covariance matrix, and you get this one spot here. It actually talks about the covariance between all of your model parameters. It's actually a very easy plot. So I am happy to talk about this afterwards if someone is actually interested here. But the main takeaway from this one here, in my opinion, is this plot here, where you are looking at the fractional percentage uncertainty on the model parameters on the x-axis, on the y-axis here. And this white dotted line is the 10% line. So as you can see, we have fairly good constraints on the X-rays, and we have moderate constraints on the UV escape fraction, and also on this star formation efficiency, the alpha SF here. But your constraints on the supernova feedback and some of the star formation ones are actually very bad. I would like to point out that it's actually a log scale on the y-axis here. So this is very bad, actually, to be honest. Anyway, so what you can do here now is that you can actually include more information into your analysis. So you can look at the UV luminosity functions. Now the main reason for introducing the constraint from the UV luminosity function is that the amount of stars in the galaxy is actually going to be much more sensitive to the amount of star formation and also the supernova feedback. So you should be able to improve your constraints on this alpha, sigma SF and also this supernova ones here. So when you do that analysis, you get this final plot here. The main point I want to point out to you is that if you look at the joint constraints of 21 centimeter power spectrum as well as the UV luminosity function, so that's the stars here, you see that we are actually able to get to 10% constraints on most of our parameters now. Yes, so in this work, we showed that you should be able to constrain your X-rays with 21 centimeter power spectrum alone. But if you include more information, especially from the UV luminosity side of things, you should be able to constrain most of your parameters with 10% accuracy. And I will stop here. Thanks.
Thank you very much, Balu. And now it's time for questions. Any questions for Balu? Yes. Oh, yes.
So, with respect to that previous slide, where you,
This one?
yeah, so
Yes.
so you're constraining these parameters connected to star formation, but can you legitimately ignore things like accretion onto black holes as sources of?
We do have AGN feedback. And sorry, carry on.
Accretion is a source of, ionizing photons.
We do have implementation of the AGN in the model. It's true. Yeah. Is already meant now.
Yeah, well, I'm just wondering. I mean, to what extent are there degeneracies between accretion as a source of X-rays, for instance, and star formation?
This is true. I'm not sure. So.
Just curious.
No, that's fine. That's fair. Yeah, that's fine.
So can you say a bit more about, for the X-rays that track star formation?
Yes.
So I mean, you have a single number for LX over SF1.
For all the galaxies, yes.
Right, but
Yes.
I might expect that, can you say a bit more about like what the actual sources of the X-rays are?
Yes, so
and whether that might actually depend on
yes,
galaxy type or metallicity or something.
Yeah, so as far as Meraxis is actually concerned, all the galaxies are of the same type in a manner. So what we actually implement for the X-rays is a model which actually scales, which is actually informed by the observations in the local universe. That actually depends upon the high mass X-ray binaries, which is why they're actually parameters with respect to the SFR, because the number of SFR scales is actually very tightly tied to the amount of SFR. Does that make sense?
But I guess what I'm trying to get at is I can envision that like the number of HMXBs formed per unit star formation.
Yes.
Might depend, just to take an example, on galaxy metallicity, because forming an HMXB depends on stellar evolution, which depends on stars overflowing their Roche lobes, and low mass and high mass, or low metallicity, high metallicity galaxies don't, massive stars at high and low metallicity don't expand at the same rate. So one could envision that the HMXB incidence could depend, for example, on metallicity. Have you given any thought to that and how it might affect your results?
We haven't given any thought to that. That's true. Yeah, that's fine. Do you have any comments?
Good idea. It's so sensitive. One thing it's sensitive to is parameters.
Yeah, I mean, at a minimum, like you can just look into the local universe, right? You've calibrated your LX over SFR, your number of HMXBs, but
yes,
do you see systematic differences between low metallicity dwarfy things versus high metallicity sparkles?
Yeah.
Any more questions? So actually, I'm really interested in the absorption stuff you showed before. So it's like,
Absorption.
yeah, is this real?
For the signal? Sorry.
Yeah,
this one?
that's one. Yeah.
This one,
Is
yes.
this the absorption of H1?
This is the absorption of the H1 signal, yes.
So it's like it lasts for.
No, that's going around here. So it's actually the Ts minus T gamma term here.
Yeah.
So the spin temperature depends upon the level population of your levels. The T gamma is the background temperature, which is the CME temperature. Yeah, sorry, you were saying.
Yeah, so that's right. So it seems like we have a long time for absorption, isn't it?
This is true, but then again, it actually depends upon the timing and the amount of the X-rays and the level of photons. We are fairly certain of what happens here, and we also fairly certain of what happens here. So this end and this end, but we are not actually entirely sure about the exact timing between the Lyman alpha and the X-rays. Yeah.
So in different models,
yes.
I can see that the absorption is there, but in the other model with a higher X-ray, we can see the emission in that case. So,
this one, yeah.
So my question is that, like in that epoch of time,
yes,
do we really see the emission or just the absorption?
Yeah, if you're asking about the high X-ray ones, if you have more amount of X-rays in the early universe, you are actually bound to see the H1 in emission here. And I think from the upper limits alone, this low X-ray one has been actually ruled out now. So we expect to see more amount of X-rays in the early universe now. Yes.
Can I just ask about the status of the edges?
Of the edges signal?
What is it? Is it actually? Is it
Where did I put it?
intentional conflict?
Oh yeah, we are not happy about this. So the reason is that if you look at the scale here, so it's actually in Kelvin. So we are looking at almost 500 millikelvin here for the dip. And I would like to point out that we are looking at this absorption dip here. And so this is from back in almost 10 years ago. So we are almost expect to see this at redshifts of 18 or so. But if you look at the actual signal here, we are actually at the same location on the x-axis. So that's fine. But if you look at the scale on the axis here, we only go up to almost 150 millikelvin. So the fact that you are seeing a much more absorption signal dip here means that if you go back to the equation, so this is the Ts minus T gamma term. So that means either your Ts is insanely cold. So that means the IGM is much colder, but that is actually not going to be the case because we have the 21 centimeter upper limits here, which says that the IGM is actually much hotter there. But the other thing you can do is you can say that instead of the background temperature being the CMB, the T gamma is something else. So you need a radio loud source in the early universe for this model to be correct. And it's also true that different teams are actually looking at the same signal and nobody else has seen the same signal yet. And they just has actually made their data open. So different teams have done the analysis in different based on the same data, and they are not seeing the same signal as well. So nobody actually, the person who you asked, I guess, but yeah.
Andrew.
On your brightness versus redshift plot, just wondering what's the range that SKA will control? It's like for your models that you showed.
What's the range in terms of the frequency or?
Yeah, that would relate to the redshift.
Yes, I am not 100% sure, but I'm fairly certain we will be able to see all these ranges here because SKA law should be able to go as low as MWA, for example, for sure. So we will be able to see all the from the cosmic dawn onwards for sure. So redshift 30 onwards for sure. Yeah, let's bring it up. Yes. So in this one, we go from 5 to 16.6, but yeah, we'll be able to see all of them with the scale.
Yeah, so you mentioned that these simulations is very expensive and something about smaller counts.
Yes.
So I was wondering if you could add, I think, this.
Yes. So yeah, the augmentation. Yeah, this is I should probably have it. All right. So what we do here, for example, if you look at this orange curve here, that's the Halo mass function of the unaugmented box. The Halo mass function is the number density of halos as a function of their mass. As you can see, if you look at the orange one here, we are able to see all the halos up to here. But we do something on augmentation and we are able to see much more smaller halos now. But the way it works is that we actually know how the halo mass function is supposed to look like from theory. So what you can do is you can actually sample from the supposed theoretical halo mass function, and you can basically introduce the halos into the box. Now, this thing has actually been done since 2005 onwards, but that's fairly good if you only want to look at, for example, the UV luminosity function, for example, because you only need to have so and so amount of galaxies in the simulation volume. But if you also want to look at the ER morphology, you need to be careful about where you place the halos, right, in the simulations. So what we do is, this is thought about these kind of things, but this is the halo method tree. So we need to introduce these halos, these new halos, such that they actually go and join onto the actual method tree from the parent body simulation. And you also need to make sure that they are actually assigned the locations appropriately, because if you don't assign the location appropriately, you won't get the actual proper your morphology field. So what we do is that we actually assign the locations based on the actual embodied dark matter density field as well for these new halos. This code is called dark forest.
So no more questions and no questions online. So let's thank our speaker again. Thank you so much, Balu. Now the gift traditional gift
Thank you.
from
I don't drink, but
but from Vice Chancellor Brian Smith.
Oh, that's cool. Oh,
yeah.
I seen this online.